You keep hearing it everywhere. More cores equal faster computers. 8 cores are better than 4. 16 cores must be twice as good as 8. Computer manufacturers love this narrative because it's simple, it sells products, and it sounds logical. But here's the uncomfortable truth. For most people doing most things on their computers, doubling your core count won't make your PC noticeably faster. Sometimes it won't make any difference at all. The core count obsession is one of the most successful marketing campaigns in computing history, and it's costing people money on hardware they don't actually need. The promise is seductive. More processing units means more work gets done simultaneously, right? Well, yes and no. Mostly no, because your computer doesn't work the way you think it does. Those extra cores aren't magic productivity multipliers. They're specialized tools that only help when the software you're running knows how to use them. And spoiler alert, most software doesn't. You're essentially paying for workers who show up to the job site but spend most of their time standing around with nothing to do. Understanding why requires looking at what's actually happening inside your processor when you click that mouse button. A processor core is a tiny, independent worker inside your CPU. Think of it as a single worker with a brain, hands, and tools. Each core can read instructions from programs, perform mathematical operations, access memory, and write results back. Modern processors contain multiple cores fabricated on the same piece of silicon, sharing certain resources like cache memory and connections to your RAM. When you have a quad-core processor, you literally have 4 separate computation units that can theoretically work on 4 different tasks simultaneously. The key word here is theoretically. Each core operates on something called a clock cycle, which is the basic rhythm at which it executes instructions. A processor running at 3 GHz completes 3 billion cycles per second. During each cycle, a core can perform operations like adding numbers, comparing values, or moving data around. Cores contain specialized circuits for integer math, floating point calculations, and logical operations. They have tiny, incredibly fast memory caches built directly into the chip to store frequently accessed data. Modern cores are remarkably sophisticated pieces of engineering, featuring prediction algorithms that guess which instructions will be needed next and prepare them in advance. They can even execute multiple instructions per cycle using parallel execution units inside a single core. But here's what matters. Having more cores doesn't automatically make each core faster or more efficient. When your processor tackles work, it can do so in fundamentally different ways. Single-core processing means one core handles one task from start to finish, executing instructions in a straight line, one after another. This is how virtually all software worked until the mid-2000s. The program runs, the core processes each instruction sequentially, and eventually, you get your result. It's simple, predictable, and for many tasks, perfectly adequate. Multi-core processing splits work across multiple cores simultaneously. Imagine rendering a video where Core 1 handles frames 1 through 25, Core 2 handles frames 26 through 50, and so on. Each core works independently on its portion, and when everyone finishes, you combine the results. This parallel processing can dramatically accelerate certain workloads, but only when the work can actually be divided this way. Here's the critical limitation. Not all tasks can be parallelized. Some operations must happen in sequence because step 2 depends on the result of step 1. You cannot speed up boiling an egg by assigning more cores to watch the pot. The egg takes the time it takes. Similarly, many computing tasks have dependencies where the next calculation requires the previous answer. Adding more cores to these sequential processes accomplishes nothing. They sit idle while one core does all the work. Modern operating systems try to distribute various background tasks across available cores, so you might see activity on multiple cores in Task Manager. But that doesn't mean your primary application is benefiting. Most applications you use every day are primarily single-threaded, meaning they run on one core regardless of how many you have available. Your web browser's rendering engine, the vast majority of productivity software, most games, and countless other programs were designed to execute on a single thread. Even applications written in 2024 and 2025 often remain single-threaded because rewriting software for parallel execution is expensive, complex, and sometimes impossible. Microsoft Word doesn't magically use 8 cores just because they exist. When you're typing a document, one core handles the keystrokes, formatting, and screen updates, while the other 7 cores sit mostly idle. Web browsing is largely single-threaded. Loading a web page involves one main thread parsing HTML, executing JavaScript, and rendering the page. Yes, modern browsers can spawn additional threads for certain tasks, but the critical path that determines how fast the page appears remains single-threaded. Even many modern games, despite improvements, still rely heavily on a primary game thread that cannot be parallelized. This main thread handles game logic, physics calculations, and coordinates everything else. Additional cores might handle audio, background loading, or secondary systems. But the core gameplay loop often runs on a single thread. Why? Because multi-threading introduces enormous complexity. You need to coordinate between threads, prevent data conflicts, and manage synchronization, all of which adds development time and potential bugs. For many applications, the performance gain doesn't justify the engineering cost. The result is simple. Software hasn't caught up to hardware, and it probably never will for most everyday applications. The fundamental problem is that many computing tasks are inherently sequential. They cannot run in parallel no matter how clever your programming or how many cores you throw at them. This is formally described by something called Amdahl's law, which essentially states that the speedup from parallelization is limited by the portion of the task that must run sequentially. If 50% of a program must run in sequence, you can never achieve more than a 2x speedup regardless of core count. Certain processes have dependencies where each step requires the output from the previous step. Calculating the 100th Fibonacci number requires calculating the 99th first. Simulating tomorrow's weather requires completing today's simulation first. Opening a file requires finding it before reading it. These sequential dependencies create bottlenecks that additional cores cannot solve. Even tasks that seem parallelizable often aren't. Consider autocorrect checking your document. You might think each paragraph could be checked independently, but context matters. A word might be correct in one paragraph, but misspelled in another depending on prior usage. Many algorithms require global knowledge that prevents clean parallelization. Then there's the coordination overhead. When you do split work across cores, those cores need to communicate. They share results, synchronize timing, and avoid conflicts when accessing shared memory. This coordination takes time and resources. Sometimes the overhead of managing multiple cores exceeds any benefit gained from parallel execution. You spend more time organizing the work than actually doing it. This is why doubling cores rarely doubles performance even in well-threaded applications. Our operating system uses a scheduler to decide which tasks run on which cores at any given moment. This scheduler is constantly juggling hundreds of processes and threads, trying to keep all your cores busy with something useful. When you open an application, the OS assigns it to an available core. When that application creates multiple threads, the scheduler distributes them across cores. Background services, system processes, and your applications all compete for core time. The scheduler makes these decisions thousands of times per second based on priority, recent activity, and load balancing. Here's the reality. Most of the time, your extra cores are running background tasks you don't care about. Windows Update checking for updates, antivirus scanning files, system telemetry collecting data, background syncing for cloud services. Your operating system will absolutely use those extra cores, but not necessarily for anything that makes your computer feel faster. The OS spreads low-priority maintenance tasks across idle cores to prevent them from interfering with your foreground work. Modern schedulers are sophisticated, but they face constraints. Thread migration between cores has a cost. Moving a thread means the new core must load relevant data into its cache, which takes time. Sometimes keeping a thread on one core, even if another core is idle, performs better than constantly shuffling threads around. The scheduler also tries to maintain core affinity, keeping threads on the same core to preserve cache locality. What you see in Task Manager showing activity across 8 cores doesn't mean your application is 8 times faster. It often means the OS is efficiently managing background noise across your hardware. The reason your PC feels slow usually has nothing to do with core count. Storage speed is typically the biggest performance bottleneck in everyday computing. When you click an application icon, your processor spends most of the time waiting for the hard drive or solid-state drive to load program files into memory. Even the fastest 16-core processor sits idle, while a slow hard disk drive spins up and seeks data. Upgrading from a hard disk drive to an SSD makes a far more noticeable difference than adding cores ever will. Memory capacity and speed matter more than cores for multitasking. When you run out of RAM, your system starts using the storage drive as virtual memory, which is hundreds of times slower. No amount of cores compensates for constantly swapping data between RAM and disk. Similarly, slow memory creates a bottleneck where your fast cores spend most of their time waiting for data to arrive from RAM. Software optimization dwarfs hardware specs. A well-written program on modest hardware outperforms bloated software on a monster CPU. Adobe Photoshop's performance depends more on how efficiently it accesses memory and handles layer operations than how many cores it can theoretically use. Network latency bottlenecks online applications regardless of your CPU. When you're waiting for a web page to load, The bottleneck is your internet connection and the remote server, not your processor. Graphics performance is often the limiting factor in games and visual applications. Your GPU handles rendering while the CPU manages game logic. In most modern games, the graphics card is the primary performance determinant. Adding CPU cores won't increase frame rates if your graphics card is already maxed out. Most performance problems are system-wide, not CPU-bound. Instructions per cycle, or IPC, measures how much work a core accomplishes during each clock cycle. It's essentially the efficiency rating of your processor's architecture. A core with higher IPC executes more instructions per cycle, completing more work in the same amount of time. This metric matters far more than core count for everyday performance. Two processors running at the same clock speed can have dramatically different performance based on IPC. A modern core with IPC of 4 instructions per cycle at 3 GHz performs significantly better than an older core with IPC of 2 at the same frequency. The modern core completes twice as much work per cycle. Architectural improvements like larger caches, better branch prediction, and more efficient execution units boost IPC. Modern processors achieve high IPC through sophisticated techniques. They feature out-of-order execution, which rearranges instructions to keep execution units busy, even when waiting for data. Superscalar architecture allows multiple instructions to execute simultaneously within a single core. Advanced branch prediction guesses which code path the program will take next and speculatively executes those instructions before knowing if the guess was correct. Larger caches reduce the time cores spend waiting for data from slower main memory. These architectural improvements explain why newer processors with fewer cores often outperform older processors with more cores. An 8-core processor from 2018 might lose to a 6-core processor from 2024, because the newer architecture executes instructions far more efficiently. Per-core performance improvements compound across all your applications, while additional cores only help the few applications that can actually use them. This is why chip manufacturers focus heavily on IPC gains with each new processor generation. Clock speed measures how many cycles per second your processor completes, expressed in gigahertz. A 4 GHz processor completes 4 billion cycles every second. Higher clock speeds mean each core executes instructions faster, directly improving single-threaded performance. For most everyday tasks, clock speed delivers more noticeable improvements than adding cores. Consider 2 processors, one with 16 cores running at 2.5 GHz, another with 8 cores running at 4.5 GHz. In single-threaded applications like most games, web browsers, and productivity software, the 8-core processor will feel significantly faster despite having half the cores. That's because the application runs on 1 or 2 cores, and those cores are completing nearly twice as many cycles per second. Real-world benchmarks consistently show this pattern. In gaming tests, processors with fewer fast cores outperform processors with many slow cores. A 6-core processor at 5 GHz delivers higher frame rates than a 12-core processor at 3 GHz in most games, because game engines depend on single-thread performance. The fast cores complete each frame's calculations quicker, resulting in smoother gameplay. There are physical reasons why high core count processors often have lower clock speeds. More cores generate more heat and consume more power. To stay within thermal and power limits, manufacturers must reduce clock speeds as they add cores. A 64-core server processor might run at only 2.5 GHz, while a 6-core gaming processor hits 5.2 GHz. Each design targets different workloads. For typical users running typical applications, fewer fast cores beat many slow cores almost every time. The exception is true parallel workloads, which most people rarely encounter. Open a dozen browser tabs, launch Word, stream music, check email. These everyday activities show minimal performance difference between an 8-core and 16-core processor. The bottleneck isn't computation, it's waiting for network responses, disk access, and user input. Your processor spends most of its time idle, regardless of core count. When you're typing, cores wait for keystrokes. When browsing, they wait for network data. Boot times depend on storage speed and startup programs, not cores. Loading applications is limited by how fast your storage can read files into memory. Even with multiple programs open simultaneously, modern processors with 4 to 8 cores handle this effortlessly. The operating system switches between tasks so quickly, you perceive them as running simultaneously. Video playback uses dedicated hardware acceleration, not CPU cores. Modern processors include specialized media engines that decode video efficiently with minimal core involvement. Streaming Netflix doesn't benefit from extra cores because the decoding happens on dedicated silicon. Photo editing in casual use rarely stresses multiple cores. Yes, applying a filter to one image might use several cores, but you spend most of your time selecting tools, adjusting sliders, and thinking about your edits. The actual computation happens in milliseconds while you work for minutes. Office productivity is almost entirely single-threaded. Spreadsheet calculations, document formatting, and presentation creation run on one core, while others idle. Compiling small programs, running basic scripts, and general software development don't stress modern multi-core systems. The performance difference between adequate and overkill core counts is imperceptible in daily use. You're paying for capability you'll never access. For most users, 6 to 8 cores is the sweet spot, with no real-world benefit beyond that. High core count processors serve specific professional workloads where parallelization actually works. Video rendering and encoding benefit enormously from additional cores because each frame can be processed independently. A 32-core processor rendering a video project finishes in a fraction of the time compared to an 8-core chip. Software like DaVinci Resolve, Premiere Pro, and Handbrake scale nearly linearly with core count for encoding tasks. 3D rendering engines like Blender, V-Ray, and Cinema 4D split render jobs across all available cores. Rendering a complex scene that takes 8 hours on 8 cores might finish in 2 hours on 32 cores. This is genuine parallel work where more cores deliver proportional performance gains. Professional users doing this work daily justify the expense of high core count processors. Scientific simulations, computational fluid dynamics, and finite element analysis use dozens or hundreds of cores effectively. These workloads involve massive datasets and calculations that can be distributed across many processing units. Researchers running simulations need maximum core counts to complete work in reasonable timeframes. Server workloads benefit from high core counts because servers handle hundreds or thousands of independent requests simultaneously. Each user connection, database query, or web request can run on a separate core. A 64-core server processor handles many concurrent users far better than a fast 8-core chip. Virtualization environments running multiple virtual machines simultaneously utilize high core counts well. Each virtual machine gets dedicated cores, allowing several operating systems and applications to run on one physical server. Data centers and IT infrastructure rely on these many core processors. Compilation of large software projects with thousands of source files benefits from parallelization. Each file compiles independently, using all available cores to dramatically reduce build times. Software developers working on massive code bases save hours daily with high core counts. What actually makes a PC feel fast in everyday use? Single-threaded performance dominates the equation. Responsiveness when clicking icons, opening menus, and launching applications depends on how quickly one core executes those tasks. A processor with high IPC and high clock speed delivers snappy, immediate responses. Storage speed is the second most important factor. An NVMe solid-state drive loads Windows, applications, and files orders of magnitude faster than a hard disk drive. The difference between spinning Rust and modern flash storage is night and day in perceived system speed. This single upgrade transforms a sluggish computer into a responsive machine. Sufficient RAM prevents slowdowns from memory pressure. 16 GB handles most users comfortably, while 32 GB provides headroom for heavy multitasking. Once you have enough RAM, adding more does nothing. But having too little forces constant disk swapping that cripples performance regardless of CPU power. A capable graphics card matters for visual tasks and gaming. Integrated graphics handle basic desktop work, but dedicated GPUs accelerate everything from photo editing to video playback to gaming. Matching your GPU to your workload delivers more noticeable improvements than CPU upgrades in graphics-intensive tasks. Low system latency creates the perception of speed. Fast response times to mouse clicks, keyboard input, and window movements make a system feel powerful, even if benchmark scores aren't exceptional. This responsiveness comes from balanced components working together efficiently. The real performance formula isn't about maximizing any single spec. It's about eliminating bottlenecks and matching components to your actual workload. Most people benefit more from a balanced system with fast storage, adequate RAM, and strong single-thread CPU performance than from an unbalanced system with excessive cores but weak supporting components. Speed is holistic, not a single number. Now, here's something that'll really mess with your setup. Ever notice how your internet just decides to quit right when you need it most? It's not random. There's actual science behind why your connection drops, and understanding it might save you from throwing your router out the window. Check out the video on screen to find out why your internet randomly stops working, because spoiler, it's definitely not random.